All right. Maybe not. Okay, thank you for this introduction. Kind introduction, see. I'm very honored to participate to this lecture series. I don't know if I am distinguished enough, but at least I'm there and happy to be so. The picture you see here is a recent photographs by a telescope called Chandra, which displays the explosion of a supernovae. You have an envelope. The red envelope singles out the presence of heavy molecules, which is torn apart and expanded by the explosion of a lighter but hot gas in the inside. And this, as you will see, serves well the purpose and the topic I will be talking about today. So, explosive fragmentation. To give you a flavor of the line of thought behind the experiments I will show, it is probably useful to go back to Pierre-Simon de Laplace, whose contribution to science, among many others, has been to understand the macroscopic shapes induced by the existence of cohesive forces between particles. So the existence of very strong attractive forces between very small particles have their counterparts at the macroscopic scale through the emergence of surface tension. This is the reason why a droplet is spherical. This is also the reason why there is a menisci on a solid wall wetted by liquid. You all know that. Our program here is in some sense at the opposite. The kind of question we will be asking is the kind of questions people like Clausius were obsessed about and are dealing with disaggregation. So this is a word of the 19th century which has disappeared, which had been invented by Clausius, who was fond of inventing names. I mean, he's the one who has proposed to use the Greek word entropy from anthropos to represents a disorder, the heat associated with the disorder. So disgregation is exactly the concept I will be talking about, and concerns all the phenomena where cohesive forces compete with disaggregation forces. You want to disaggregate something which is cohesive, and then you wonder what the fragments will be. This is all about, I will be talking about. Okay, so in order to address this, we've made an experiment, and because we want to, we like to understand every step of the process, we start with the geometry, which is as simple as possible. So what we see here is a bubble, liquid shell, which is formed in a way I will describe momentarily, and which is filled with a reactive mixture, so hydrogen and oxygen. By a way that you'll see later on, we ignite the mixture at the center of the bubble. There is a chemical reaction. As you know, hydrogen and oxygen produce water vapor at high temperature, and therefore the burnt products occupy a volume which is larger than the initial reactants, and will therefore explode the bubble, expand the bubble, precisely because the volume occupied by the products is large. Okay, so the result of the experiment is the following. You have an expansion. You have not seen the spark igniting the mixture, but you'll see later on. The envelope increases in size, expands. At some point there are holes, as you've seen, which appear on the envelope, and then the envelope bursts in a set of disjoint fragments. And because the initial geometry is simple enough, our ambition is to describe the expansion dynamics, to say something about the shell stability, and to describe also the hierarchy of fragments which are formed. So, remember my introductory slides. We're in a situation where cohesion, we're expanding a liquid which is cohesive. Cohesion competes with disaggregation forces. As a matter of fact, this experiment had been suggested to us by reading the famous treatise of Marangoni on la bolle liquide. I don't know if some of you speak Italian. I don't, but I have tried to do a traduction. As you know, Marangoni was a teacher. He was teaching kids in small classes, and he was demonstrating the explosive, the detonant character of hydrogen with oxygen by inflating a bubble, soap bubble, letting it ascend in air, and then with a wick bursting the bubble by firing the mixture. And as he mentions, the most spectacular effect is obtained without any danger from the ignition by firing wick of a soap bubble inflated with the mixture as it ascends into air. So since this is safe, we can proceed. So this is the way the liquid shells we're exploding are formed. This is a process which has been suggested and studied by Kendall in the 80s. We're sending the mixture we like to fire into through a jet into a liquid envelope, which results from the destabilization of an annular jet of liquid. So the liquid is essentially water with a little bit of glycerol. And as you can see, you have a capillary instability. This is a typical capillary instability of dripping, if you like. Thus isolating a bubble which is filled with the mixture at the desired composition. And it turns out that this process produces shells which are typically 10 microns, a couple of 10 microns in thickness, and with radii which are a couple of centimeters. And there is a one-to-one relationship between the radius and the thickness, so if we can vary both. All right, the experiment is simple in its principle, but this is not exactly a tabletop experiment. I mean, it sits in the middle of a couple of apparatus. There is a laser which ignites the mixture. This is by a spark of a laser that we fire the mixture. It is aimed at the center of the bubble. When the bubble passes inside two lenses, realizing a Schlieren system. The Schlieren system is interesting because, as you know, it is able to track for very slight density differences, density gradients. And this is convenient to us because we like to see at the same time the evolution of the liquid shell, which is easy to see, and the evolution of the reactive region of the flame itself, which is much more difficult to see. So this is the reason why of this Schlieren apparatus. When the bubble arrives at the center of the system, the laser shoots inside it, and all this is recorded at a high frame rate. All right, and as I said, we want to describe the overall fragmentation pattern. We want to understand in particular the reason why the holes appear on the shell. their typical density, why and what is it controlled by. And once the whole are formed, we want to understand also the dynamics of the rims of these holes when they merge, and the ultimate formation of droplets. All right, so interface dynamics. The flame first. So the same kind of experiment can be done in a soap bubble, like in the Marangoni style. And you have seen, so it's quite fast, but you will have another chance to get it, which is even faster. As you can see, there is a flame which propagates at the center, inside the bubble, and typically as the flame reaches, or just before it reaches the initial envelope, the envelope bursts. This parameter phi is well known to combustionists. This is called the equivalence ratio. And the speed of propagation of the flame is extremely sensitive to it. So a mixture is set stoichiometric when the relative proportions of hydrogen and oxygen are optimal. This is also in that case that the propagation speed of the frame front is larger, is the largest value, and away from this optimum, the radius of propagation of the flame, its velocity decays. So it's very interesting. This dependence is very interesting because this is, for us, a way to play with the parameters. This is a controlling parameter, which is quite interesting because, as you will see, the speed at which the flame increases in radius is what is controlling the stability of the liquid shell. Let me replay the movies now that you know the story. Be attentive. All right. And then even faster when the mixture is closer from stoichiometry. Okay, so this is faster, and again, because I think I have control of this, yes. So you recognize a soap bubble. This is the laser spark. The flame propagates at constant velocity, and as it is about to reach the initial shell, the shell bursts. Okay? All right. So that was for the flame. The liquid interface itself. Okay, you've seen the spark. The liquid interface itself has an extremely violent motion because it departs from its initial value, R naught, at a rate which is itself a function of time. I mean, the difference between the radius and with the initial radius is proportional to the cube of time. So this is extremely fast, extremely violent. And the violence of this motion is responsible for the destabilization of the shell, as we'll see. So okay, we have a standard propagation of the flame with a constant velocity, function of the equivalence ratio, and then a strong, very strong motion of the liquid shell. Let's try to understand this, and in particular the physics ruling the expansion of the shell, this T-cube dependence. So, as I said, the objective was to be in a geometry which is as simple as possible. So we have here essentially a spherical expansion, so only one spatial coordinate and time. And the velocities are such that they are much, much lower than the propagation of sound in all the phases. So the Mach number associated to the motion you've seen is low. We don't expect the formation of shocks or extremely sharp density gradients due to the motion. So the motion is approximately close to incompressible. The pressure scale is thus the one given by the propagation of the flame itself. So rho B is the density of the burned gases. Rho U stands for the density of the unburned gases. And since the flame propagates at Rf dot, Rho U Rf dot is a kind of a stagnation pressure ahead from the flame front. Flame front is pushing essentially the whole universe ahead of it. So we have a shell of thickness h, and the rho infinite is the density of the outside medium. So the pressure scale is that. The recall pressure, an object which is well known from combustionists. I hope I don't run. An object which is well known from combustionists is the pressure difference across the flame front. So a flame is essentially a surface of discontinuity between two media with different densities and different velocities as well. Thus, since fluid particles cross this interface, the motion is accompanied by pressure difference. But that pressure difference at the scale of the source pressure of the motion is extremely weak. So we won't take it into account. Of course, we have a liquid shell, so there is a Laplace pressure associated to it, a pressure jump due to its curvature. But again, seen at the scale of the pressure driving the motion, it is ridiculously small. And as for viscous stresses, they're proportional to the velocity of the motion. We've seen that the radius is strongly accelerated, meaning that the velocity is itself a function of time. Velocity is a function of t squared, so that at short time, the viscous stresses are not expected to be important at all. They're evanescent. All right. So this inventory is interesting because it basically tells all the effects we won't be taking into account. We have simply thus a Rayleigh-Plessey dynamics. The flame pushes, as I said, the media ahead of it, and its motion, the motion of the different phases, is well described by a kind of a Euler equation. This is a Rayleigh-Plessey dynamics. So that relationship can be integrated along the radius r. R equals 0 is the center of the bubble. And the pressure at the flame front is useful at pushing the medium made of unburned gases. It is useful at accelerating the shell, the liquid shell itself. And it's also useful at accelerating the outside ambient air. But at short time, so the pressure front can be, the pressure of the flame front is computed, and it turns out that at small time, when the flame radius is smaller than the shell radius itself, that term is obviously dominant, so that at short time, the evolution equation for the radius is simply proportional to the cube of the ratio of the flame radius to the initial shell radius. And indeed, the different trajectories you've seen before are nicely rescaled in these units. The expected trajectory, so the 1/4 here, is the dashed line. As you see, it overestimates a little bit the true trajectory. The reason is that we have neglected compressibility in the system, which is fair, as we can see, but which is not exactly true. If the process is safe, it is nevertheless noisy. I mean, you hear an explosion, you hear a deflagration. So there is a little bit of compressibility associated to the problem, and it is possible to have the compressibility corrections to the basically incompressible description I have just given. But that description is fair enough for us because with the properly recovered T cube, we will be able to address the stability physics of the shell. So precisely, the stability. We start with a shell with radius L0, and at some point, at some time, when the shell has a radius R of T star, we see the appearance of holes in the shell. And then these holes progressively grow, merge, leaving the initially convex liquid shell into a set of disjointed droplets. So it's useful to understand the origin of this process. Of course, the instability responsible for the destabilization of the shell is a Rayleigh-Taylor instability. The reason is that the motion of the shell is extremely violent in the radial direction. It is violently accelerated. There is this T cube, and T cube is a strong acceleration. And if you accelerate strongly a liquid interface, it destabilizes. Okay? So the process we have is a little bit different from the infinite liquid depth limit, which I am just making now, because the film thickness, the shell thickness is finite. In fact, in this kind of problem, there is an acceleration R double dot, from which you can construct a capillary wave number, the inverse of the capillary scale, which in the standard Rayleigh-Taylor instability gives an estimation. Gives a fair estimate of the distance between the unstable structures. So it gives the wavelengths, the preferred wavelengths of the instability. However, we have another length scale, precisely the thickness of the shell. And when the thickness of the shell is thin enough meaning that the product of KC by H is smaller than unity, which also says that the thickness of the film is much thinner than the spontaneous Rayleigh-Taylor wavelengths, then not only the growth rate of the instability is affected, it goes to zero as H goes to zero. So a film which is infinitely thin is essentially rigid. But the selected mode is a mixture of the natural, let's say, Rayleigh-Taylor wavelengths and of the film thickness itself. So that was realized soon after the contribution of Taylor to the Rayleigh-Taylor problem by Keller and Kolodner, and this is what it looks like in an analog experiment. As you see, the wavelength is larger than the initial film thickness, and at some point these things will break, leaving the initial film as a set of disjointed droplets. So it's a 2D experimental analog I could describe. So yeah, that's the way the dispersion relation is deformed. This is the traditional infinite depth limit, and this is how the dispersion relation is deformed when the film thickness is thin. And as you see, this privileges large wavelengths. All right, so the acceleration is itself a function of time, because the radius goes like T cube, meaning that the acceleration is itself proportional to time, so that the growth rate of the associated instability, the one I have just described, the Rayleigh-Taylor thing, is itself a function of time. So when will the shell pierce? Well, it will pierce, as usual in this kind of problem, when the gain of the instability is over the 1, and the gain of the instability is the integral of the growth rate over time. Essentially, in this kind of problem, you spend most time growing disturbances in the linear regime close to the initial state, and the final events of the piercing are associated to phenomena which have a much smaller, much shorter characteristic timescale. So the important thing is to understand the initial destabilization, hence this piercing criterion. Okay, doing the corresponding computation, there is a number which appears, with which some of you are probably familiar, which is a Weber number, which compares the inertia with the capillary confinement, and it turns out that the characteristic time of the destabilization of the envelope is essentially the time it takes for the flame to travel on the initial radius of the shell times a correction which involves this Weber number, a weak correction because the power is 1/4. So this is the shell as it is initially. An instant after, one sees a little bit of corrugations. They are more obvious here. And an instant after, the holes have pierced. And we have a network of ligaments, which we will describe later on. All right, for the same reason, the radius of destabilization is essentially given by the initial radius of the shell, and the correction is weak. So the piercing time indeed follows this minus 1/4 power law. The Weber numbers are of order 100, and yes, the radius of destabilization is essentially R0, consistently with the observations. All right, for the same reason, the discussion on the mode selection has to account for the fact that the acceleration is itself a function of time. It turns out that the most amplified wave number is proportional to time at the instant of destabilization. This predicts an evolution of the most amplified wave length of this Rayleigh-Taylor instability as a function of the Weber number, which is essentially recovered. And you see that this is a number of holes recorded in real time on the shell. The number of holes increases and then decreases, and this destabilization time is essentially the beginning of the recordings here. All right, this is what the shell looks like. This is a strong expansion, so a large Weber number, a moderate one, and a weaker, milder one. And you can see already here an interesting feature is that when the distance between the holes is larger, the roughness of the ligaments, those which are the prelude to the drops, I am anticipating a little bit, the roughness of the ligaments is larger than when the distance between the holes is smaller, which suggests that the drop side distribution will be a little bit different depending on the Weber number. All right, so precisely fragments. We have described the typical distance between these holes. We have understood why they appear, an acceleration, an inertial instability. We have now to wonder what produces these drops. So at the stage where we are now, it's quite obvious. The rims of these opening holes, and you understand why they open, because if you make a hole in a liquid sheet, locally the surface tension forces are normal balanced, and if they are normal balanced, there is a retraction which is driven by surface tension, therefore explaining the expansion of the hole. And the hole, as it grows in radius, collects in its rim the liquid which was initially constitutive of the shell, thus producing ligaments. And at some point the ligaments collide with those coming from the neighboring holes, and from this collision results corrugated, more or less corrugated ligaments, which in the end break by a capillary instability. But The typical diameter of the ligament is simply given by mass conservation, given the density of the holes and the thickness of the shell at the moment of bursting. This is just that the liquid inside two holes has been drained and concentrated in the ligament. This is a simple geometry. And what we know also, since Rayleigh and Plateau, is that if you have a ligament which is given by DL, you also have average drop sizes which are proportional to DL. All right. I was in fact discussing this kind of problems, the generation of the origin of drop size distributions from corrugated ligaments a couple of years ago in this institute at the invitation of somebody who is in the audience. And I remember that I displayed this graph. It's the same. That was at the invitation of John Bush, and I explained that the drop size distribution coming from the breakup of ligaments is following always the same distribution. It's a distribution which has this form, which is called the gamma distribution, when the sizes of the droplets are seen at the scale of their average. And that the only parameter which matters in this problem is the initial state of the ligament. If the ligament is corrugated, you get a broad distribution of sizes, while if the ligament is smooth, you get a distribution which is more peaked around the average. And this is exactly what we have here, because as you have seen, at least qualitatively, when two rims are coming from far away, receding at a given velocity, if they're thick as they collide, they're likely to dissipate more energy, to corrugate more the ligament than if they're nearby with a smaller distance to travel and are therefore lighter as they collide. So this is the reason why when the density of holes, the network of ligament is smooth, the ligaments are smooth on the network, and this is the reason why intermittent and diluted holes give rise to extremely corrugated ligaments with a broader distribution. All right. So the drop sizes, you see the process, the collision process online. As expected, the drop size distribution follows a gamma distribution. And this is what I have just said, which is now imaged and illustrated by pictures. When you have a large density of holes, you have smooth ligaments. When the density of holes is smaller, the collision is dramatic. By the way, it even produces a liquid sheet in the other direction. So that's a very interesting process, which is currently studied precisely, and produces a much broader distribution of sizes, which shows here. These are the two distributions obtained, and distribution of sizes, again, rescaled by the average, corresponding to two very different hole densities, and you see that one distribution is narrower than the other. The green dots corresponding to this situation, the black one to this one. And of course, the non-interesting quantity, because it is obvious, is the average drop size, the one which serves as a rescaling quantity here, which follows the obvious mass conservation. All right. So we have basically characterized the overall transition, disaggregation process from an initially convex liquid sheet to drops. Given the initial thickness of the sheet, its initial radius, the initial composition of the mixture we have, we are able to predict completely the drop size distribution in the end. However, I know that some people here in the audience are interested in dispersal of spores, for instance, from plants or from fungi. So that's a drawing which is reproduced from the famous contribution of the Pope in the system in this area, who is called Ingold, and who has consistently measured the not the drop size distribution, but the spore size distribution ejected by these vesicles in fungi. So the spores are nested in a kind of envelope, and not only nested, but they are also glued with each other by a kind of a mucus. And the resulting spore size distribution is like that. It looks like very much the distributions we have seen before. I will do it in the old style by sitting in front of the audience. And there is very probably a Darwinian explanation to the fact that there is a distribution of spore size or spores ensembles. Because a fungi, if the species want to as you know, the bottom line is fight for life, right? If you don't fight, you die. So everybody knows that. At MIT, especially, the point is that one way not to die is to reproduce yourself. Okay, so if you want to reproduce yourself, your interest is to eject spores in the area where you are already, because it's a good spot. You have something to eat. You have been able to produce these spores. This means that you're healthy. So you want to give a chance to your descendants to use the same spot. And this is the reason why for the big bags here, because when ejected at a given velocity, they won't go far. Now, the spot will not last for forever. So you need to do exploration as well. So you need to give a chance to some of your spores to explore larger regions. And this is the reason for the small spores, because the small spores will be driven by the wind to explore other spots. So this is the reason why, at least reading Ingold, the interest of having a distribution and not a single size. Anyway. Another example is the eggs in nests which are impacted by raindrops. So some researchers have wondered what the impact of a raindrops on an assembly of objects close to each other would result in, and you see that this poses the problem, like that one, of the future of the disaggregation of an ensemble of objects which are linked by something, capillary bridges here, a kind of mucus there. So let's, as an extension to the experiment I have described before, look at that experimentally again. So the idea, the philosophy is exactly alike the one I have described previously. We'll start with the simple geometry. It is even simpler than the one we have seen before with the spherical shell. We'll consider a ring, a necklace of magnets which are connected to each other. And we'll, as with the explosion, we will enforce the expansion of this ring and wonder how the system will react to this forced expansion. Yeah. Okay. So this is the experiment. You have a ring of magnets, so spherical magnets, which is sitting on a cone, falling by its own weight, and at some point the cone hits the ground, thus forcing the expansion of the cone. Okay. So let's look at the same phenomenon from the top. All right. So as you see, initially the system, maybe I can replay the movie. Yes. So yeah, at short time, the necklace is completely dismantled, completely disaggregated. And as the fragments separate to each other, they remember that they are linked by a long-range force, which is the magnetic force. So it's really a trade-off between expansion and cohesion, exactly our topic, the Rudolf Clausius obsession. And you see that from the trade-off of these two ingredients, expansion and cohesion, results an inverse cascade. Not a direct, but an inverse cascade. And that's absolutely unlike the phenomena we have seen before. Initially, the magnets are separating, and very rapidly they coalesce. And as they are embedded in larger and larger fragments, it takes the fragments a longer and longer time to be attracted to each other and form larger and larger islands. And at some point, the fragments are so large, so heavy, and so distant to each other that they don't attract anymore, and the system is atomized completely. So the atomization process we have here is an inverse cascade from the smallest sizes towards the largest one, and that cascade is interrupted at some time. So this was with a given number of beats, with a smaller number of beats corresponding thus to a larger initial divergence. Obviously, the divergence is stronger, the magnetic attraction is still the same, so that the final fragment is smaller. We have a control parameter here, the initial divergence. All right, I'm not going into much details. As you probably all guessed, this is liable of an extremely precise description because the geometry is simple, the physics of the attraction is extremely simple. This is a dipole-dipole interaction, so the force law is 1 over x4 if x is the distance between two magnets. And again, we have a Weber number which measures the relative importance of the initial divergence. U is this divergence versus the compared to the intensity of the attraction. Of course, the larger the Weber number, again, the smaller the fragments will be. All right, let me just illustrate with graphs the temporal evolutions of, for instance, the fragments mean size. It, as we have seen qualitatively, it increases in time and then reaches some asymptote. This is where the cascade is interrupted as a function of time. And also there is, if V denotes the radial expansion of the ring, we see that there is a deceleration at short time and then a constant velocity. The existence of this deceleration is just a manifestation of what we would call the surface tension, because this is exactly the same origin. If you're an aggregate here in the vicinity of two aggregates nearby, you see that their attraction gives rise to a net negative force retaining you in your radial exploration. So this is the reason why the velocity decreases, because there's a net force opposing to the radial expansion. All right. All this can be quantified, but more interesting is the evolution of the not drop size distribution, but fragment size distribution versus time, because all this, as you've seen, is recorded in real time. So initially, as we've seen, the sizes are small, typically 2-3 units with a distribution around it. And as time proceeds, so it proceeds in the direction of the red, the distribution gets broader at the same time its average increases. So not only the average size increases by this aggregation process, but also the heterogeneity of the assembly is larger. So by this random addition process, which is random, you have not justified, but it's random, and there is no correlation to the size. The population gets more and more heterogeneous. However, if you see the population not for itself, but at the scale of its current mean, then the distribution becomes universal. In other words, you just need to understand how the average size increases in time, and once you have done that, you're just left at understanding the shape of the distribution. But in these units, the shape of the distribution is constant. And it turns out that, of course, it's a gamma distribution for the same reasons we've seen before. It's an aggregation process. The physics underlying the construction of the distribution is a random aggregation process. This is the same physics which was responsible for the formation of the droplet sizes coming from the breakup of a randomly corrugated ligament. Exactly the same kind of physics. All right. Okay, so these equations are silly. They are just here to convince you that standard, not Archimedean, I have Archimedes there, I think, not Archimedean, but Newtonian dynamics can describe the system. It's very easy. I mean, you take two subsets of the two islands of size p, q, and you can write down all the equations describing their trajectory. The k ratio in this problem is involves the Weber number. There is an escape velocity. The escape velocity meaning that if you're heavy enough and distant enough, you will never reconnect again. The aggregation cascade proceeds until fragments reach their escape velocity. So, as I said, when they are distant enough and divergent enough. So divergence competes with cohesion. We were talking about that a couple of minutes before this lecture, and therefore the size is proportional to the control parameter, the Weber number to the power of -1/3, a result which not only fits our observations, but which is just a raw formulation of something which was discovered by Grady a long time ago. Some time ago. We were born at that time. Some of us. All right. I won't annoy you too much with the fundamental origin of the gamma distribution. I have said that already a couple of times. It's just because it's a random aggregation process, and the random aggregation process produces distributions which are stable with respect to the random addition of the variables, and the family of distributions representing this fundamental addition law in the variable space are gamma distributions. The peculiarity here is that a small aggregate, which is light, is more likely to aggregate to a big aggregate in its vicinity than a bigger one, because precisely the bigger one is more heavy, and the time it takes for the heavy fragment to aggregate will be larger, owing to Newton's law. And in fact, you realize that all fragments which are smaller than typically 1/3 or 0.27 the mean are liable to be instantaneously or very rapidly aggregated to others in their vicinity. And if you realize this, you also realize exactly at the same time, this is a general theory of incomplete convolution that I have. This corresponds to an order of the gamma distribution, which is exactly the one we are showing, we are measuring experimentally. So gamma distribution of order 8. All right, but I see some of you wondering when I stop. No, not really. Okay. But one objection to what I have just showed is to realize that the magnetic forces, so the dipole-dipole interaction, is a long-range interaction. Long-range meaning that it involves power laws. We know, including in the examples, the Ingold examples, for instance, I have shown, we know that if the particles are linked to each other by something else than the long-range power law, but by a liquid bridge, for instance, the attractive interaction will stop at some distance because simply the liquid bridge has broken. Okay. So if you think also about the translation of this kind of ideas to the problem of fracture propagation in solids, the particles I have shown being atoms. We know that the forces attracting the atoms have a finite range. So, is it possible to do the same kind of experiment, but with a different force law, a different attraction between the particles? So the answer is obviously yes. If instead of magnets we consider gel beads, which are linked to each other by liquid bridges precisely. And if you find a way, this is not easy, but we can do that. You find a way to organize them in kind of a necklace by assembling them by a bubble. So this is a very fragile object, right? It is self-assembled by a soap bubble. So really the capillary forces are strong enough to assemble the thing. You realize pretty much the analog of the magnet experiment, except that you've now changed the fact that you have no more a long-range interaction, but a very short-ranged attractive force through this liquid bridge. All right. So let's see what happens. So this is quite difficult to do. You have to put as you see, the necklace on a deformable substrate, which is impacted gently. I mean, this is not this is easy. But as you see, there is obviously the formation of islands of aggregates, and if you are attentive enough, for instance, in this region. I remember. So you see that one breaks. So those two will never talk to each other anymore. Those two wanted to escape, but they have been attracted back to this bigger fragment by the retraction of the capillary bridge. Okay, so that although the force is different as previously, the phenomenology is identical. All right. So, not surprisingly, we fall on the same kind of distribution of fragment sizes, except that we have no more an order which is 8 as previously, but an order which is lower. And if you remember, a low order corresponds to a broader distribution. And the broader distribution, there is a difference with the magnet's case anyway, is that the strength of attraction between two nearby gel beads is given by the size of the capillary bridge. And there is an heterogeneity in the size of the capillary bridge, so that the strength is itself fluctuating from one bead to the other. As you impact the system, the liquid, it's a mess. So the liquid reorganizes somehow from bridges to bridges. So that there is a distribution of forces. There is defects in the material, in the sense that the force strength is not as uniform as it was previously with the magnetic case. And this explains exactly the reason why we have a broader distribution. So the dots in blue are exactly the same experiment with the magnetic beads we have redone after that distribution with the gel beads. by introducing, by heating more or less the beads. And when you heat the magnet, as you know, there is a temperature due to a French researcher called Curie. There is a Curie temperature. And if you are close to the Curie temperature, the magnetization, the spontaneous magnetization disappears. So by heating more or less our beads, we were able to change the intensity of the forces, to introduce a randomness in the intensity of the forces between our magnets. And we did so in order to mimic exactly the distribution of volumes we had on the gel bead experiment, so that the intensity of the noise, the width of the distribution of the forces linking the magnets is the same as or reproduces the one in the gel bead experiment, and as you see, the variance of the distribution is the same. So it's really the heterogeneity of the strength which is responsible for the broadening of the distribution. However, this distribution is still described by a gamma distribution precisely because it originates from an inverse aggregation cascade. All right. So what's the take-home message, as you say? The usual vision inherited from Kolmogorov, for instance, of fragmentation is that you go from the one big size initially to stable fragments which are smaller and which have been the result of a sequential cascade of breakups. A mother drop breaks into two outer drops, which themselves are mother to smaller, and so on. So the arrow of time is directed in the same direction, I should say, as the sizes going from large to small. This is the usual picture. Which is okay. I mean, the sequential cascade of breakup is the one you have in the mill in mills, for instance. It's or if you take a stone, you hit it with a hammer, you collect the pieces, and you redo the same thing sequentially. This is what will happen. However, in the situations you've seen all along this talk, you've seen that an initially connex object was transitorily disaggregated in atoms, and that the final fragments in fact resulted from an inverse cascade, and that the arrow of time, this progression of this cascade, was directed from a process involving the smallest available sizes initially to a size which is larger than the size of the fundamental atom. Some processes interrupt the cascade. This is what makes the final distribution of fragments. But by no way you have seen in the transient a direct cascade from a big object to a small object. So that's in some sense the general message summarizing the different observations I have shown. Thank you.
Do you have time for questions for those that can stick around? Yeah?
Yes, I was wondering about, in your exploding bubble experiments, you use clean fluids, so you use water and glycerin.
Exactly.
What happens if you use surfactant? Does the spectrum change?
So we have not added surfactants in the shell experiments. We have been using surfactants to create these soap bubbles. Okay, measure the flame thing. The reason why we are using these shells is that they're approximately 10 times thicker than the usual soap film. Okay. As you know, a soap film is typically a micron thick, and it's impossible for us with our limited means to measure the drop size distribution coming from the bursting of a micron thick liquid shell. So this is also the reason why we moved to this liquid shell, thick liquid shell system.
Right.
And in that case, we have not added surfactant at all. So I don't know.
What would you anticipate would happen?
Nothing. The time are so short, the time scales are so short that the surfactants will probably sit there and will do nothing. I have no time to do anything. In the experiments we did some time ago on the Sava sheet, as you know, introducing surfactant in the liquid had exactly no consequence on the size of the sheet, precisely because the surfactant had no time to come back to the surface and decrease the surface tension of the liquid. So even with a surfactant loaded in the liquid, you recover the size of the pure water, the sheet size corresponding to the one of the pure water. So I don't expect much changes by adding surfactant.
Has anyone done those experiments where you do approach Mach 1? So you can get, if you have a spherical shock funding, you'll get faceting. So that would introduce a new length scale in the column.
Yeah, sure. But
No one's done those?
no,
No.
not yet.
Yeah.
Other questions?
When you have surface tension, if you go on the small length scale, you're introducing also a different physics. So maybe for your one set of experiments that you showed, you might get the same answer, but just having surface tension and a fluid and so forth, does that really explain how you could take a fluid body and make a hole in it? That you have just the hole appearing. You did linear stability theory,
Yeah.
and a hole appeared.
Yeah, sure.
But you didn't talk about the physics
Of hole formation.
and that is a disintegration.
Sure.
Of
Sure. No, you're absolutely right. I have not described at all the physics of the hole formation in itself. I have just described the time it takes to make a hole.
Assuming that physics is not entering and your Navier-Stokes equations and your surface tension dominate.
It does not, by the way, because the van der Waals forces are operating.
Exactly.
Yeah,
so
yeah, but
you could be fortuitous that you chose a certain set of problems that.
no, you're absolutely right. I'm not dealing with disruption. I'm not dealing with the very last instance where the change of topology occurs.
So
I absolutely agree, but I am absolutely right to do so.
that's
Yeah.
I'll defend your right to do it. But just one short thing: if you had a flat film of finite thickness of liquid, not too thick, okay? And then you very quickly made a very small radius hole in it that was small compared to the thickness. What would happen to the hole?
It will heal.
Yes. Okay. And there's a critical size.
Yeah, the critical size being given by the sheet thickness itself.
Okay.
That was described by G.I. Taylor.
Yes, in the 1970s.
Exactly. One of his last papers. One of his last papers and one of the first he published in the Journal of Fluid Mechanics.
In the Journal of
Fluid Mechanics. It's a journal. Sorry.
that one of his students started.
Other questions? Yes, please go.
I think it might be relevant to the last question. So the analysis for domain instability that you did was based on Rayleigh-Taylor instability mechanism.
Rayleigh-Taylor-Kolodner.
Yeah. And you assumed you get a constant wavelength, and then but the videos you showed, some of them at least, you could see a distribution of the drops or holes basically, which is very similar to the patterns you would see in, for example, duvetting. If you go to nucleation dominated, thermal nucleation dominated.
Absolutely. No. Very good question. So you've seen that the holes do not all appear at the same time. I had so the number of holes, the net number of holes present on the shell, first increases. There are some happy fews which arrive at the beginning, and then more and more. But at a given instant of time, those which had nucleated before have expanded, so they leave less space for new holes to appear. And so this is the reason why the number of holes decreases in the end.
As you go to a more uniform one, you get something more of a Gaussian distribution.
It's not a Gaussian, but it's a bell curve, sure. So all the holes do not appear at the same time. They do not appear on a regular pattern. You're absolutely right. And this is due to the initial thickness modulation that you have on the film before it is accelerated. This we do not control, and this is due to noise, thermal noise, exactly. So that's the point. You're absolutely right. It's a distributed phenomenon. However, as you have seen from the number versus time curves, you can clearly identify a bursting time.
Okay, maybe one last question. Anybody has a burning one? Discussion.
Burning H2O2?
Yeah. You're. No? Okay, well, thank you very much.